All right, welcome back everybody. In this video, we'll be doing just a couple of examples from section 8.1. The first thing I wanted to mention though is how you can do confidence intervals with hypothesis tests. So a confidence interval estimate from chapter 7 of a population parameter contains the likely values of that parameter. Therefore, it makes sense that we should reject the claim that the population parameter has a value that isn't included in the confidence interval. So you could calculate a confidence interval and then based on whether or not that interval contains whatever the hypothesized value is, use that as a basis for either rejecting or failing to reject that null hypothesis. All right, so just a couple of examples of different parts of calculating or doing a hypothesis test. So in this first one for 3, we want to just answer the questions. So here it says a formal hypothesis test is to be conducted using the claim that the mean body temperature is equal to 98.6 degrees Fahrenheit. What is the null hypothesis and how is it denoted? So I would say the null hypothesis is, well, equal to, our null hypothesis contains equal. So mean body temperature equals 98.6 degrees. Okay, the alternative, in this case, I don't have any reason to suspect that it's either less or greater, so I think it's simplest just to say not equal to 98.6. And then the possible conclusions that can be made about the null hypothesis are either that we may fail to reject it, or that we'll reject it. Okay. Is it possible to conclude that there is sufficient evidence to support the claim that the mean body temperature is equal to 98.6 degrees Fahrenheit? And the answer there is no. We can't really prove or support H0. Our alternatives are either just to reject the null hypothesis or not reject it. And there's a difference between not rejecting something and saying that it's true. Okay. All right, so here we're for number 5, which is the claim is that 20% of adults smoke. A recent Gallup survey of 1,016 randomly selected adults showed that 21% of respondents smoke. So express the original claim in symbolic form. So I would say that P is equal to 0.20. That's a proportion, right? 20%. Identify the null and alternative hypotheses. So the null hypothesis always contains equality. So we'll have that as 0.20. So then the survey showed that it was 21% of adults, which sounds like more than 20%. So I'm going to go ahead and use greater than 0.20 because looks like our sample data is greater than 0.20. We just have to decide if it's significant or not. Okay, more setting up hypotheses. A battery manufacturer claims that the mean battery life is 60 months. We want to try to show that it is less. So the null hypothesis is 60 months, right? And it's about a mean. So that's mu. Mu equals 60 months. We think it's less, so we'll go with less than 60 months as the alternative. Okay. A little more calculation soon. In each of these, we're going to find the value of the test statistic. So let's see for our first one. It says 3/4 of all adults believe that it is important to be involved in their communities. Based on this poll of 1,021 adults, 89% believe that it's important to be involved in their communities. So we're to calculate a test statistic. So you have to read this and decide, what is this about? Is this about a mean, a proportion, standard deviation? What is it about? The claim is about 3/4 of adults. 3/4 is like 75%. So that sounds like a proportion. So that's going to be our claim, okay? So then we didn't need to do it for this, but we may as well. Let's go ahead and put down the two hypotheses that P is 0.75, and then here in this poll, it was 89%. So I'd probably go ahead and put this bigger than 0.75. So test statistic. So we need the test statistic for a proportion. And that Z is equal to P hat minus P divided by the square root of PQ over N. Okay, P hat, that comes from our sample. And so that's 0.89. Then the P here is the one from the hypothesis. So that's 0.75. That's over our square root. PQ, P is again from our hypothesis. Q is 1 minus P, so that's 0.25. And that's on top of N, which is our sample size of 1,021. So let's go ahead and compute that. So bear with me while I work the calculator. All right, so I got 10.33, which is pretty large. Okay, let me just double check and make sure that worked. Okay, yep, that does turn out to be a Z of 10.33. I was surprised by that because it's really large for a Z value, but in a way it makes sense that we've got 1,000 people here and 89% believe that had this belief, and the hypothesized value is 0.75, so that's quite a bit lower. Well, we got it. There's our test statistic. All right, so for 15, it says the claim is for adult females, the standard deviation of their white blood cell counts is equal to 5. So the claim is about standard deviation and that it's equal to 5. So we'll go ahead and put in the two hypotheses here. So our null hypothesis is that the standard deviation equals 5. The data shows a standard deviation of 2.28, which is less. So I would go with less than 5 as the alternative. Then we needed a test statistic, right? So for standard deviation, it's chi squared, which is n minus 1 s squared all over sigma squared. So here, the sample was 40 females. So 40 minus 1 is 39. Our sample standard deviation was 2.28. And that's over sigma squared. And that sigma is the hypothesized value. Okay. From the null and alternative hypothesis. Okay, so this time 8.1. One actually, for our test statistic. Okay. All right, so that was 15. Now we'll to see 16. For this one, for adult females, the mean of their white blood cell counts is equal to 8. A random sample of 40 adult females in the appendix has a mean of 7.15, so that is our X bar, and then a standard deviation of 2.28. Okay, so we need the test statistic. The claim is that the mean is equal to 8, so that's our claim. So the mean is equal to 8. So then our alternative is that it's not. It looks like it's actually lower at 7.15 for our sample, so less than 8. All right, so here, notice in here that the population standard deviation is not known. So we're going to be using a t-distribution. We're talking about the mean. That's what our claim is about. But we're told that the sigma is unknown, so we're going to be using the t-distribution. So we'll have x bar minus mu divided by s over root n. So the X bar comes from our sample. The mu is from our hypotheses. And then the S we're given is 2.28, and that's over the square root of n. Our sample size was 40. Okay, so this will give us our test statistic. And that's negative 2.36. All right, so when you're reading through a question, you want to decide, okay, what's the claim? Is the claim about a mean or a proportion or a standard deviation or a variance? If the claim is about a mean, you need to decide if the sigma is known or not, to decide whether or not you're going to be using the Z or T distribution. Okay, all right, so here we're practicing and finding p-values and critical values. We'll do number 17 here. We're going to assume for each of these examples that our alpha is 0.05. So for 17, we're given a test statistic of 2 that, when testing the claim that p is greater than 0.5. So critical value method. We're told that our alpha is 0.05. We're testing this claim that p is bigger than 0.5. So that means it's a right tail test because it's got a greater than in it. So that means our right tails should be 0.05. Okay. So then if our right tail is 0.05, then it's going to be 1.645. That will be our critical value. Okay, so now we want to go about finding the p-value. The critical value we saw was 1.645. Okay, for p-value, okay, again, I'm going to start with a picture. Okay, we got a test statistic of 2.0. So we'll take, and that's positive, right? So our test statistic is 2. So let's look in our Z table, right? We're testing a proportion, so that's Z table, and we're given Z here. So we're going to look in our Z table for the area associated with a Z of 2. So that's 2.0.9772 is the area to the left. So then 1 minus 0.9772, because again, we want the right tail. And so that's going to be 0.0228. So this will be our p-value. Okay, so notice on this, for the critical values, we started with alpha of 0.05. We use that to work backwards to get a critical value. And then for the p-value, we took the test statistic we had and looked in our correct table to find the corresponding area. And that area is our probability. Okay, so now we want to try 20. So here it says the test statistic of 1.50 is obtained when testing the claim that p is not equal to 0.25. So we're going to start by drawing a picture. This one is two-tailed. Okay, so then our test is two-tailed because it's got a not equal to in it. Our alpha we were given was 0.05. So that means if we're doing a two-tailed test, we're going to have 0.025 in each tail. Okay, so if it's 0.025 in each tail, that means that the area to the left of like the rightmost cutoff is 0.975. And so looking in our table for that is going to be 1.96 and also negative 1.96. So the way that, then that's our critical values are going to be plus or minus 1.96. So the way that the hypothesis test would work is we'd say, okay, well, our test statistic was 1.50 here, which is not in one of those shaded regions. So we're going to end up failing to reject whatever that hypothesis was. It didn't say. Okay, because our 1.50, which was our test statistic, didn't fall into one of those two tails. Okay, so now we'll be doing the p-value next. So for p-value, again with the little picture, our test statistic was 1.50. So 1.50 here. And then we're going to find the area in that tail. So again, looking to our Z table, it's 0.9332 to the left. So then 1 minus 0.9332. So that's 0.0668. Okay, that would be the area in one tail though. And our test was a two-tailed test. And so we're going to double it. Okay, so 2 times 0.0668 is 0.1336. Okay. And so on this one, notice that our p-value is 0.1336, which is bigger than our 0.05, which was our significance level. And so again, we would fail to reject our H0. So notice that our conclusions here in number 20 are failing to reject for both of those. Regardless of whether you use the critical value method or the p-value method, you're going to get the same overall conclusion regardless. Okay, one more example. We'll do 23 here. So here it says, assume that the significance level is 0.05. Use the given statement to find the p-value and critical values. So here, the alternative is p is less than 0.6 and our test statistic is -3. So critical value method first. Okay, so this time it's less than, so it's going to be a left tail test. We'll have an area of 0.05 in the left tail. And so if it's 0.05 in the left tail, then that's going to be -1.645. Okay, and that'll be our critical value. Okay. For the p-value, we'll take a look at our test statistic, which was -3. And then we want to know the area to the left of -3. And that should be pretty small. 0.0013. Okay, so that will be our p-value, 0.0013. All right, so then to compare, that's it as far as the question goes, which was just to calculate the critical values, but let's go ahead and check what conclusions we will get out of this. For the critical value method, the test statistic, it was -3. -3 is in our rejection region, right? So we would reject the null hypothesis. Okay, for the p-value method, our 0.0013 is less than our alpha of 0.05, so again, we would reject our null hypothesis. All right, so that's the end of that. I just wanted to do a few examples from section 8.1 so that we'll be ready to work on 8.2 next. Let me know if you have any questions and have a great day.